Today's lesson is on properties of polygons. You've seen quite a few polygons at this point. So a polygon, let's write down the title, Properties of Polygons. A polygon is a 2D shape with 3 or more sides. So you already know about triangles, which have 3 sides, quadrilaterals, which have 4 sides, and then we can do up to 10 sides, and you should know the names for each of those. So got a number of sides, and name. So make sure you've got this written down first of all. Pause the video if you need to. A polygon is a 2D shape with 3 or more sides. We already know triangles have 3 sides and quadrilaterals have 4 sides. A 5-sided shape, do you know what that's called? It's a pentagon. 6-sided shape, what do you think? Hexagon. A 7-sided shape. Anybody think they know this one? That is a heptagon. An 8-sided shape, octagon. 9-sided shape is a nonagon. And finally, a 10-sided shape is a decagon. So get that copied into your books, please, and you should try to learn those names. Okay, so those are some different names of polygons. We are now going to have a quick look at symmetry and interior angles. When we talk about the interior angles of a polygon, they are the angles inside of the polygon. So the interior angles of the triangle are all of these angles. They're the interior angles and they will add up to a certain value. In this case it is 180 degrees. The interior angles of this rectangle are again at all of the corners or all of the vertices, and in this case the interior angles add up to 360 degrees. And for this pentagon, again, is at the vertices or the corners of the shape, and in this case the interior angles add up to 540 degrees. We're going to write down the interior angles of a polygon are the angles inside the polygon. So get that written down, please, and copy the diagrams as well. The next thing I want to look at is reflectional symmetry and rotational symmetry. If we have a look at this example, so this should be a regular octagon, and it should have 8 equal sides and 8 equal angles. Now, how many lines of symmetry does this have? It has 1 here, because this side is a mirror of this side. it has one here. It should have, if I'd drawn it well enough, another one there and another one there. So that's 4 so far. And that's going through each of the flat edges. We've then actually got ones through each of the vertices. So it ends up with 8 lines of reflection symmetry. Reflection symmetry is where we have lines that cut the shape in half and one side is the exact mirror image of the other side. So that is what reflection symmetry is. So let's write that down. So reflection symmetry is when one half of the shape is the exact mirror image of the other half of the shape. So pause and write that down, please. So as an example, if we had an equilateral triangle, we'd have a line of symmetry here, because this half would be the same as this half. We'd have a line of symmetry here, because this half would be the same as this half. And it would have a line of symmetry here. So that would have 3 lines of reflection symmetry. However, if I had an isosceles triangle, that would have a line of symmetry here, because these 2 sides would be the same, but it wouldn't have any other lines of symmetry. So that would only have 1 reflection line of symmetry. Rotational symmetry is where we can rotate the shape and it will sit exactly on top of itself. So if I take this shape and I rotate it so that this line and this line move round to here, if it were a regular octagon, it should sit exactly on top of itself. And again, we could rotate it here, here, and here. Rotational symmetry is how many times you can pick it up and rotate it slightly and put it down, and it would sit exactly on top of itself with no lines or shapes showing behind the new one that you've picked up and rotated. An octagon has rotational symmetry of 8 because you can pick it up 8 times and put it down on itself. If I take a triangle, an equilateral triangle, I'm going to label these sides 1, 2, and 3. I could pick this triangle up and I could rotate it so that side 1 moves round to here, side 2 moves round to here, and side 3 moves round to here, and that would give me 1 rotational symmetry. I could then pick that up and switch it round again so that side 2 has moved from here to here to here. Side 1 has moved from here to here to here. And side 3 has moved from here to here to here. If I then pick it up and rotate it again, I get back to where I started. So that means I can pick it up and rotate it 3 times to get back to where I started. So this has rotational symmetry 3. And we do count the time that we pick it up and rotate it and it gets back to where it was in the first place. If, however, I have an isosceles triangle, and I label the sides 1, 2, and 3, I can't pick that up and rotate it to put it down on itself because it's an isosceles triangle. So this short side 3, when I pick it up and rotate it, would end up here, but it wouldn't cover the whole of the triangle. So I would end up with something that looked like that. And you can see this is not covering this because now the short side is where one of the longer sides used to be. If I pick it up again and rotate it, I have the same problem on the other side. The short side is now here on side 2. And then I'll have these 2 long sides. So again, if I rotate it twice, it doesn't sit back on itself. However, if I rotate it all the way around so that we get back to the beginning, it will sit perfectly on top of itself. So this has rotational symmetry of 1, because in a whole 360-degree turn, it only sits perfectly on top of itself once. So, writing this down please, rotational symmetry is the number of times a shape sits exactly on top of itself when you rotate it by 360 degrees. So you take a shape, you rotate it slowly through 160 degrees, and you record every single time through that rotation that it sits exactly on top of itself, and each one of those would be rotational symmetry. Finally, we've got tessellation. So tessellating patterns are tiling patterns with no gaps. So for example, if I put a load of of equilateral triangles together, if they're exactly the same size equilateral triangle, I should be able to tile them together like this with no gaps. So copy that down please. You can have a go at drawing your own tessellating pattern if you like, and that should be enough for you to have a go at the question sheet.